So, good afternoon. Today we are going to talk about more molecular geometry. If you have your molecular geometry 1 and you have any questions, I'm going to go through a problem. So if you'd like to go through one of those with me, that'd be great. But a couple things. Molecular geometry 1 is due tomorrow. Your job, your assignment was to get to that line. Okay, it was supposed to get to that solid line, and we were going to teach you the other stuff today, which we will. And that will be what we're going to be working and focusing on tomorrow and tonight. So that's what you're going to be working on tonight and bring questions for tomorrow. You have identifying bond lab. Many of you still need to get in and take it and do it. You can't wait 3 weeks and then all of a sudden make up a lab. We got to put chemicals away. So I know just out of my tour, I have like 9 people still haven't taken it. You gotta do the lab. We make a list of who wasn't here. You gotta be active in that. You've had 11 days since the ending of lab to do, I think, 6 or 7 post-lab questions. So that is due by tomorrow. But you could have handed that in early, and you've had 11 days to do that. For some of you might be starting that tonight. The post-lab has been sent to you a while back, so it's the covalent versus ionic lab. So that is also due tomorrow. Hopefully you've already have that in. We are doing a geometry lab Friday and Monday. Friday we're using our iPads. Monday we are doing ball and stick models, so you actually are going to manipulate them yourself and kind of be able to see it. So one using the screens, pre-made models, the other one you have to create them. And then in 2 Fridays we have a test. Today is basically the last day we are teaching you anything new. Say that again. Today is basically the last day that we are teaching you something new, and you have now a week and a half that we are going to be practicing this stuff in different ways. I've told some of my classes before, and I'm serious about this, over about a 15-year period, these tests are usually A's or they're F's. And the reason why is that students either have worked on it. There's a reason why we give you a week and a half, because it takes time. You have to practice. You have to go through problems. You have to sometimes actually have some failures and realize, oh my gosh, that's how you do that problem, or this is how you do that problem. If you're going to come in on that Thursday or that Wednesday, we will try to help you as much as possible, but if it only took 2 days to teach it, we would only teach it in 2 days. So the frustration that now you're feeling or that you'll have, it's legitimate, but you need to kind of reflect inward, because the whole point of it is that we're giving a week and a half of basically practice and review, and again, there's reasons for it. It's tricky. It's hard to conceptualize and see it. So we got to practice. So please take that to heart. And you have a chance. It's not like, well, I didn't do well on my periodic table test. It has nothing to do with it. You can still bounce back and learn all this. But that's in 2 Fridays from now. So, that all being said, let's actually hook up my computer correctly. Too many cords over here. I think that I have that. There we go. That's the good noise. All right, so anybody have a question? Front or back? I will do one. So first come, first serve. I want to go through one just to make sure that we are moving forward. This is our worksheet from Monday. Well, I had said it a couple minutes ago, yes, but you don't have to. I'm going through a problem if you'd like to. I'm just doing it for you if you'd like to go through a problem. So many people. Yes, yeah. 19, good number. This one's hard. So this is the one we're going to do. If you don't have your sheet, well, just follow along then. 19's tricky. Any of them that have multiple center atoms doesn't follow the standard rules. So first, don't let this shake your new but hopefully developing knowledge of the molecular geometry. It'll take some time. But in general, I'm going to write it nice and big here. I hope that we kind of think symmetrically. I would have, this is all based on our Lewis structures that we've already done. I have 2 N's and 4 Cl's, so it would kind of bond like that. Okay? 9 times out of 10, most of these structures that we're dealing with will bond the standard way. What I mean by that, I don't have to do all this TV stuff all the time. How many times does N like to bond? Looking at that. That likes to bond 3 times. Try to keep it that straightforward, like a carbon. Likes to bond 4 times. If you can try to satisfy those kinds of situations in a structure, you don't have to do a lot of other legwork. In this case, look at 1, 2, 3 bonds. 1, 2, 3 bonds. That's kind of probably what is already going to happen. So basically what I have then is I have the 2 CLs. It's just kind of my scratch work. And then I do have this right there. So I put the dots on top. And I've made 8 for my center atoms. If you're really unsure, some of you won't want to go down this path all the time, you could count all this up. 4 times 7, right? Because chlorine is 7 from last chapter with the valence electrons. So that'd be 28 plus 5 times 2 is 10. So I should have 38. I could add all this up. So these are all worth 8. I could add them up, and I'll actually get that number. It'll be 38. But I'm wanting to try to focus you on this. If it bonds 3 times, I feel good about that. Carbon bonds 4 times, I feel good about that. What's the goal? These are why these are hard. I have 2 center atoms. So I have to make it like it's 1 center atom. Like either one counts. So the whole point of this chapter is about clouds. Center atoms, how many clouds? So I have 1, 2, 3, 4 clouds around that one. Or I have 1, 2, 3, 4 clouds around that one. It doesn't matter. It gets me to the same final answer, which is I have 4 clouds. So we talked about the term steric number is the number of clouds around your center atom. Why is that important? Today we're going to hammer this home, but it's about the thing called parent geometries. Now we gave you a sheet called a Vesper sheet, which will be a reference sheet. Let's not get confused and think that we're going to have that on our test. We would have that on our test. We wouldn't need a week and a half of work. We would need like 2 days because you would just use that. But 4, a prefix for 4 is tetra. And here, we learned last week, valence shell electron pair repulsion. Every time you add an atom, it repels. So that repels, that's 3. You add another one, it repels it away, right? You remove it back. Whoop, hey, get back here. It springs, kind of messed that up. It springs away. So it's all about repelling with electrons. So I have 4. It's called a tetrahedral. We're trying to make it look like a tripod. So this is in the plane, this is in a plane, this is coming at me, this is going away from me. So basically, this is what's hard. If it was just an N, it would be up, over, at me, away. Here's the problem. There's 2 of them. So that's why this one's harder. So I have to kind of connect them and then make this one come at me, go away, come up. Come at me, go away, come up. And then these are my, CLs, not Fs. So that's my structure. What's the next column? Is it parent geometry? I can look at it. Oh, whoops, I'm sorry. That should have been there. So the minute I say 4, it's the word tetrahedral. I'm out of room. Shoot. It's all one word. But if there's lone pairs, it's not a tetrahedral. Today I'm really going to, I think it helps a lot. I'm going to teach you how all these names really work with each other. But there's 3 of them. There's 3 bonds besides the lone pair. So there's a trigonal and it's like a pyramid. So this is what we call a trigonal pyramidal. Believe me, this would not be the first example I would use if I was trying to teach this. Like this is not a clean example. This is harder. Bond angle? Is that the next one? I don't know. Okay. Bond angle. If you memorize 109.5, the other ones you shouldn't have to memorize. Tetrahedral is 109.5. Not friendly. I get it. Not a friendly angle. But every time you add a lone pairs are bigger. They push harder. So if you add a lone pair, it pushes it down a little bit more. You add another one, it shoves it down a little bit more. Shoves it down by 2% every single time. So 109.5, add one, 107. Add another one, 105. So I've added 1 lone pair above this. So 109.5, the one that we remember, pushes it down to 107. Okay, we're gonna be doing all this again today. Lastly, not all of us got hybrids the other day. That's okay. I'm not here today to tell you all the meaning behind it. It gets very, very complicated. Just understand this. Electrons come from S's and P's and D's. And they all have to make the same angles. It's not like one angle can come from an S and another can come from a P, because then you'd have different angles from one bond to the next. They're all the same angles. So they create the same bonding. So we call them a hybrid. So they come from these letters. So all you got to do is say, how many clouds do you have? I have 4 clouds. So every cloud comes from one line. So I always say S, but you can only say S once because there's only one S line. We've learned that in our electron configurations. So then you start saying P's. So with 4 clouds, it would be SPPP. So that'd be SP3. If it was 3 clouds, you'd say SPP. So it'd be SP2. 2 clouds, SP. You'll see the trends if you didn't go through that before. Great question. Horrible example if I'm actually starting off. But we're not, because we did do this on Monday as well. So it's a tricky one. We're not going past that line until the end of today, though. So if you have more questions, I'll try to help you. But note sheet, if you're doing it on your iPad, great. We are going to get going. Because we're going to practice that more tomorrow. We're going to answer questions like we're still focusing on that worksheet. Okay? So, what is an octet? I'm going to write this up in the upper left. This is where 8 comes from. When we say octet, that's why you have 8. I'm not making you write a lot because I typed out a bunch already on there. So I'd write this in the upper left. Today we are going to break the octet. The only way you can break an octet is if you can hold more electrons than 8. How can you hold more electrons than 8 if you only have S's and P's? So, what they have found is that center atoms, I want you to highlight a couple things with me here. Center atoms in the 3rd energy level can break the octet. What happens in the 3rd energy level? The 1st energy level, you have S's. The 2nd energy level, you have S's and P's. What do we gain in the 3rd energy level? What are all these? Those are transition metals. What sublevel is that? It's a D. Now you're like, well, yeah, but if you're in the 3rd row, you don't have that yet. True, but it's like they purchased a storage garage and they have the ability to store something in there if their uncle stops by and gives them something and they have no room for it. It's the D sublevel. They have that ability to have that overflow. Here's my boat. You want it? Sure. Throw it in your garage. You have that ability to hold it. So if you ever see like C, N, or O on the 2nd row, that can never break an octet because it literally can't hold any more electrons. So today, we're going to try to break the octet. Or we will. So, this has not gone so well, but I'm going to try it again. I'm a killer at kids' birthday parties. They're like, make us molecular geometry. I'm like, you want a trigonal planar? So, here's 2 clouds. That is a linear. Right, they get as far away as possible. Okay? You bring in another one, what does it do to the other 2? It repels them, right? And now now there's 3. So now they're as far apart as possible. We'll do this simultaneously. So there's 2. You add another one, it repels it, right? You take it away, it springs back. All right. So now, on Monday we added, we added a 4th one. What happens? It pushes down, right? Valence shell electron pair repulsion. It will push down, right? Oh, come on. Springs back, pushes down, springs back, pushes down. All right, here we go. So, check this out. If I even hold it like this and then I just shake it, it automatically goes to that. It's not like it's just random and it's fake. They are as far apart as possible. It is called a tetrahedral. I'm going to talk about this later, but why it's called a tetrahedral? Hedral means surface or side. There are 4 sides to this structure. But what happens if you have 5? So, what happens when I bring this one up from the bottom? What's it going to do to those other 3? It's going to push them back up, right? It's going to push them back. Come on. It's going to push them back up. Now, I've not made this stick yet. And you be the first. Shake it. Woo! It's a good day. Going to the casino. No. I have, what do I have? I have this these two balloons going straight up, and then what kind of looks like is going on in the middle? What shape? In the middle. What is that in the middle? Looks like a triangle. Kind of. I know this doesn't as much. This is great. Believe they've been all falling apart. It's been a disaster. So this is awesome. So it looks, you don't have to draw this yet, but it looks like this in space. It takes this kind of double pyramid with a triangle in the middle. Okay? So what's going to be nice, we're going to make two really complicated shapes by just basically saying, hey, it's a stick with a triangle in the middle. That's one of them. Here's the other one. If I add another one, that's what happens. And I'm going for it. See. What does it make? So close. Look at that. Look at that. Oh. What shape is in the middle now? It's a square. Okay, so we're going to talk about that. And why are they making these shapes? It's not because they're choosing to do so. They're getting as far away as possible. So we're going to draw them all in a much easier way. Okay, but it'll look kind of like this, where there's this square. It's this square in the middle, and then this axis going right through it. So let's see how we're actually going to draw it. So this is it. Where? Oh my gosh. So parent geometry. You have a sheet that has 14 drawings. I'm here to tell you that all 14 come from 5 shapes. We're drawing the same 5 shapes all the time. So the first one, 2 clouds. If I have 2 clouds, they're as far away as possible. What did we call that yesterday? Or Monday. I'm going to keep saying yesterday. That would be linear, right? So that would be linear. So I would draw it like that. I'm not putting anything at the ending of my bond lines. The reason why is that those could be atoms, those could be lone pairs. It doesn't matter. This is where those electron clouds, those densities, these balloons, are going to be. We call it linear, and I'm writing the hybrid. 2 clouds, 2 letters, SP. I'm making sure I'm doing my fingers in the right order. 3. So you add another one down, pushes it down, and we learned that that would be called, we already learned the first 3 on Monday. Trigonal is always when there's 3. It is in a plane. I'll come back. I'll come back. It's in a plane, so that's why it's planar. So I just draw it like that. I mean, you could get really fancy and try to draw it flat, but there's no reason to do that. I have seen people don't do this because we do these 3D, and then they're like, it trails away. It's right there. And then it's like, it's in your face. So it's all like flat. Don't draw that. I have no idea what I'm looking at. This is flat on the board. And then the last one we had is we added another one, pushes down the other 3. There's 4 of them. We learned, like Tetris has 4 pieces, but it's more the hedral part. There's 4 sides. I'm going to do it live for you right now as well, in case you always forget this. You put the center atom, you go up, over, out, away. The illusion is that we're trying to make it look like a tripod. We're trying to make it look like it's a tripod, but this is in the plane of my board. This is coming out at me, so it gets bigger. Please draw it the right way. A lot of people are doing triangles the wrong direction. And this is fading away, so this should get smaller. Don't stress out about it, but try to do it as much of the correct version as you possibly can. So up, over, out, away. That's probably the one that's done the most in first year chem, because a lot of structures are tetrahedrals. They just are. All right, and then the last 2, and we're going to practice them a lot. And again, it's SP3, right? Clouds. SP, SP2, or SPP, SPPP. So that's 4 clouds, 4 letters. Last 2. So this is how I would draw this. So I'm going to, oh shoot, I can't do it. You draw a line, just put an X. If you want to see it from scratch, just in case if that's confusing. Put an X, put a vertical axis. And now for the most complicated 2, this is all you got to do. Either I'm doing a triangle, so you put a line to the right, and then you have it come out a little bit and come out over. I'm not drawing it like this. Like, don't do it like this. Like, woo! Like, it's not a flat triangle this way, it's a triangle this way. It's perpendicular. Wait, where's my triangle? There it is. It's perpendicular. So we're trying to make an illusion that it's flat. So try to bring those together. It's trigonal bipyramidal. Why is it that name? The base is 3, so we always say trigonal. And then there's, don't draw this on yours, but there are 2 I know that looks ugly, but there's 2 pyramids. So bi for 2 and pyramidal for a pyramid. So trigonal bipyramidal. But we're going to delete that. And then lastly, the other complicated one, instead of saying that there's an axis with a triangle in the middle, we're going to make an axis with a square in the middle. Why is it called an octahedral? Again, hedral means face or surface. There's actually, think about it, there's a square pyramid. So if it's a square, there's got to be 4 sides of the pyramid. There's 4 sides on the top. There's got to be 4 sides on the bottom. 4 plus 4 is 8. So you have 8-sided shape. Why SP3? I should have said these before. SP3D, 5 shapes, or 5 clouds. SPPP. Why can't I give more P's? You can only have 3 P lines. My 8-year-old son would think that is the funniest line in the world. But anyway, D. Just thinking about him right now. Keep me giggling hard. And then 6, I'm derailed. 6 clouds, S, P, 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 D, D. So SP3, D2. So that's what we're working on. All the shapes are based off of these 5. That's it. And we're going to be doing them a lot. And I'll show you how we're going to apply it when we actually do some practice problems. So I'll give you a second more to get that down. And we're going to move on to bonds and polarity. We'll practice a little bit on the back. We'll do a couple examples and we'll be done. All right. I'm going. Here we go. So let's talk about bonds. There's a lot more depth to this than what we're going to teach. But for now, we just need you to be able to identify them. So this is sigma. I'm just seeing if I do in parentheses. I did not. Whoa, we don't want that color. This is a sigma bond. That's the symbol, though. This is a pi bond. A sigma bond is a single bond. A pi bond is a multiple bond. So we're going to do 3 examples. What are my examples? Oh, you're there. Let's do those 3. All right, so right now, honestly, this is not a test of what if you know these shapes or not. Oh, I see the problem. Sorry about that. Let's do the same problem twice. Sorry. So, P has 5 valence electrons. So you'd think that it could bond 3 times. And with that lone pair, it makes 4 clouds. So, 4 clouds, tetrahedral, up, over, out, and away, right? But I don't need to worry about that really. It just looks like this for bonds. I just want to identify the bonds. If I had to label something to be easy, I don't like saying the word, but if something was easy, this is the easiest things to do, the pi and the sigma. You will fly through your worksheet. It takes about a minute. Once you understand it, if you have something drawn already, it just goes. We just have to understand what it is. So here's my pi, or my sigma and my pi. A sigma bond, or a pi bond, is what it says. It's a bond. And a bond is electrons being shared between atoms. So, that being said, this is not a bond. Even if there's a line there, those are electrons. You do not count those. So, that being said, every bond has 1 sigma bond in it. It is the bond that the electrons are overlapping and where we're sharing, and we have those covalent bonds where we used Lewis structures and we shared everything. So I see 1, 2, 3 single bonds. So those are all sigma bonds. There are no double or triple bonds, so automatically this is 0. You only have pi bonds if you have double or triple bonds. So when I don't see a double or triple bond, automatically pi bonds are going. All right, let's talk about how the next one works. This is how this one looks. Remember when carbon bonds and wants to bond 4 times, why are my hydrogens kind of at an angle? Because it's a trigonal planar and they want to get as far away as possible. If they go straight out, there's space that they could move. Okay, how many pi and sigma are on here? So sigma, pi. Here's another hint. The number of bond lines that are drawn has to equal the number of sigma and pi total. So I see 6 total lines. Where? 1, 2, 3, 4, 5, 6. These two have to equal 6. Every bond has 1 sigma bond in it. So every bond, 1, 2, 3, 4, 5. Every bond has 1 sigma bond. I don't know if the top one's a sigma, but I'm just going to call it that. Every extra bond is considered a pi bond. 5 plus 1 is 6. I have 6 bonds. Jump to the last one. Based on the very short amount of information I've given you already, can you tell me how many sigma and pi are on there? If you're using pencil or on the tablet, take a shot. Like actually write it out.
1 sigma.
Don't tell me, no. You do it yourself. Don't want to give away the secret. What do they have to equal? Add it up together. 3, right? If you at least equal to 3, you're on the right track. So, is it 1 and 2 or 2 and 1?
1 and 2.
1 and 2. It's always 1. Always 1 sigma bond between atoms. And again, don't have the time or the ability to go through this right now because it's not the important thing for you, but just think of it this way. The space between here, all of it's sigma. Pi's go above and they do other things, but there's no room. So whatever's going on here, there's only room for a sigma. The pi are these extra bonds. And that's all you need to know for now. They're the extra bonds. So that's how we do that. Okay, so that's bonds. We're going to go to polarity. Hopefully you have that down. I'll give you about 10 more seconds to have it, if you don't. That was about 8 seconds. We're going. Here we go. Polarity. Jeez, everything's off. All right. I forgot the examples I'm doing. Oh yeah, CO2. Here we go. Okay, I don't know if you remember this or not, but it's this thing called electronegativity. It's a fancy way of saying that electrons are being pulled from one atom to another in a bond. So I'm just making a generic little periodic table right now. Oh. Do you remember who has the strongest? I'll just write it. We'll talk about it all later. Oh, jeez. F's the largest. Like, if you can just remember that arrow. See if I can, there. The more to the upper right, the stronger it is. And that's going to be important for us in a second. So, you need to know what the shapes are. We'll talk about what that looks like. Okay, so I'm going to draw them all out here. So that's what the two structures look like. And structures matter. If you drew this bent versus linear, it changes the polarity. What is polarity? Polarity, whenever you hear this in chemistry or science from this point forward, polarity is about poles. Think of poles like charges. The Earth has a north and a south pole. Magnets have poles. So one end of an atom could be positive and the other end could be negative. That's a big deal because then it could be attracted to things. One side could be attracted to compared to the other side, and it helps dissolve salts and structures. It helps our bodies. Actually, we wouldn't be alive without this. Okay, we made you do this. If you don't remember, it's fine. You'll get it back. We have to draw bond dipoles. This is called a dipole. Remember, this side was positive and this side was negative. How do I remember the positive? It looks like a positive. And all I have to do, if I want to simplify this, I just put the arrow towards the one that pulls harder. So the one that's closer to the upper right. So between C and O, O is closer to the upper right. So I don't draw it on the bond, just put it above it or below it. The electrons are going to be pulled towards that O. But the electrons are also going to be pulled towards that O. For P and F, well, F's easy because F is the strongest electronegative atom there is. So it is the most upper right. Noble gases don't count. So they're all being pulled like that. What's the point? The point is, are the electrons being pulled in a synergistic way, meaning all in one direction? Are we moving negative on one end of the atom and positive on the other? If vectors work for you, things cancel out or work together. Think of tug of war. Are they moving in a direction or not? Traffic, are we moving in a general flow or is there like gridlock? Well, in this case, they're totally canceling each other out, right? So they're not like moving in one direction because they're moving in two different directions. So, whoa, where did that come from? That would be considered non-polar. So meaning no poles. This thing would not have any charge. And usually, things that are symmetrical are not polar. I'd really make sure you write that down. That's absolutely vital. I'm trying to simplify this into the most bare bones ideas that we can. If you look at the other one, though, it all kind of looks like they're moving down somewhat. So we can draw a generic or a general average and say, you know what, they're all kind of going down that way. This is called a dipole moment. And basically, if you can draw that, you can say it's polar. And usually things that are polar are asymmetrical, meaning that they're not all even. If you're not good with symmetry, an easy way for you to do it is just take your hand and you put it vertically. Does it look like it's a mirror image? Put it horizontally, above and below your hands. Is it a mirror image? In this one, when I do it this way, I kind of have F's on each side of my hand, and the P is the same. But if I do it this way, I have F's below my hand, but a lone pair above my hand. It's not the same. It doesn't work all the time, but it's one way you can kind of approach it. So that's polarity. Once you have that, you can flip the page. I'm actually kind of excited about this next part. I've never done this before. I think it's really helpful. You guys have 14 shapes, and a lot of times over the years, students seem to just have troubles with the names. So my job, I hope, today will help you with how and why the names are how they are. What you're looking at right now are the first two rows, so I'm writing in between them. It looks like there's like 3 rows on your note sheet, okay? We're going to be writing in between the first 2 rows. So I'd suggest doing and drawing on the structures the way that I'm doing it, personally. So these first 3 all have a triangle, right? All have triangles. And what word have we been using for triangle? Trigonal. So all of these would use the word trigonal. This is not meant to be a crazy, confusing concept map. What it's trying to do is just show you the relationship of very few amount of words to many geometries. take a look at another one. These two have squares. So we say the word square. The two on the left, if I hold them in my hand, they'll touch my hand, every single atom. So what word were we using with this one at least? This is trigonal planar. It's all in one plane. Well, guess what? This one's called square planar. So square planar, trigonal planar. It's the name of this one. Everything basically has two names. Again, I'm just showing you where these all come from. If it ever rises up, this is where it starts to get a little weird. It kind of looks like a pyramid. This is where now you got to make a decision how much you want to cover up the other stuff. But when we say the word, when we look like there's a pyramid, we've been saying pyramidal. And in this case, there are two. So this is called a a square pyramidal. This is a trigonal pyramidal, and this is a trigonal bipyramidal. They all link to names. Okay, my fear, if this is confusing you, my fear isn't that I'm trying to confuse you. All I'm trying to show you is that all of these structures come from only a few words. So this isn't going to be like a sheet that you're going to like constantly like, oh, this is my sheet I'm studying. Like this is the one. But with all of these, I mean, I'm not writing a lot of words down. And there's more structures than this. And then finally, just so you have an understanding, hedral means sides. So I have 4 over here, I have 8 over here. So tetra and octa. And I don't want to even draw on it, but there's 4 sides because, well, I'll draw on it. You can make a decision if you want to. The 2 fronts, the back, and then underneath. And here there's front, side, back, front, side, back. I drew it on here last hour. It did not look good when I was done. So there's no point for me to do that. So if it works for you, great. Or at least gives you the idea that, hey, these names don't come from 7 different completely independent names. They come from only a couple words. The last 4, and I know some of you are still writing, all come from names that reflect exactly what they look like. Exactly what they look like. I'll come back if you're not done. This is a line. It's linear. This is actually bent. This looks like what letter? Looks like a T. You got to turn your head. And then my favorite one. Seesaw. If you haven't been on a seesaw for a while, it's or a teeter-totter. I grew up as a teeter-totter. I did not do well on teeter-totters. People would get off really fast, and then I'd fall down hard. I always lost. I didn't know it was a game. Apparently, it was a game, and I never won. That's all I know.
It was? I just had fun.
Or you trust them. You trust them. You're like, you both think you're doing it, and then one's like, ha ha ha, and then they stand like, you gotta.
Always me.
Yeah. Okay. Let's see if this hour does a little better. I have confidence in this hour. If a ball's coming at you, you have to catch it. Okay. You can't. If it hits you, you have to go. I'm not trying to play dodgeball. Here's just how it works. I will do the easy one. If you think this is linear, it'll snap back. All you got to do, your job, if you get a ball, I have dodgeball, I have a tennis ball, and an awesome-looking soccer ball. You have to get one to make it spin. So, what? And if I let it go right there, I feel good. All right? So, if you get one, you come up, just pick any of them you want. If you don't get it right, you got to get one to get the spin. So you got to move it around or grab a different one. Okay, then you can throw, please. Last hour someone just, I think they were upset they had to come up and they just chucked it without making sure people are looking. So the ball's coming to you. You have to catch it. Go up. Oh, no. No. Oh, it did. Did it not hit you?
It was in a weird direction, like he put his hand from...
Whatever. You make it work. Come up, put one, give it to someone else. You like deflection. This will take a minute. You, as you're sitting here, kind of be thinking about what they are, though, because you might get the ball next. Or think about which one you want to get. I'll get this one. Oh, you have to bring it to it. It's not that sophisticated. Try again. Yay. All right. Yes. Almost broke it all. Oh, that one's been having problems. You're right. It's been having problems. That one doesn't like it, so, okay. Yay! If you get one, go! Like last hour, literally, this person was just walking and just chucked it, and they like bounced off the 3 people. You got any of them you can pick? Yay! It's so satisfying to see the spin. Like, no, I'm start. Oh. That one's a triangle on the bottom, not a square. You can find the square one on the bottom. Oh, that should have worked. Try it again. That should have worked. Oh no. There's 4 there. What? No. That one has 4 on it. So that one has 4 coming off of it. So which one it deals with 4?
So that would be.
So that one has 4 on it, so you can pick the one that says the word 4 is a tetra. There you go. Yay! Only 3 left. So whoever has the tennis ball, you're the last one. Whoever's what?
Yeah, there you go. Okay. You want this back
Yeah.
then? Okay.
Thanks. Player. That was a tough one for you. All right, good job. So we should know where these are. And if we didn't do it, hopefully we're at least dreaming of it, one or the other. So on the bottom, I'm going to do 3 quick problems with you. These will mirror a worksheet that will be due by Wednesday. It's actually very short. Most of you will be done much earlier than that. So do these with me. They're right on your sheet. I'm going to show you how we do this now from formulas, and then we're done. We're just doing these 3. So I hope we agree that we don't want to write in white. So we put AS in the middle. Now, I don't care about the shape right now. I hope we all agree that there would be 5 atoms bonded to it. Now, that's all I would do, and I'm going to push you to that's all you're going to do as well. But for sake of notes, for right now, I'm going to do one of these. On the end of each of those, I call them a spoke. Each spoke has a BR with all those dots. So basically, what does a spoke equal for electrons? What is each of these going to equal? They're all going to equal 8. Right? I'm hoping that eventually you get to this point where you're just like, oh, that's 8, that's 8, that's 8. I'm just trying to figure out number of electrons right now. Reason why. Let's just put that back. My question is this 5 clouds or could it be 6? Why could it be 6? There might be a lone pair on there. Lone pairs are important. I have a pair hanging in my room. That's how important it is. And it's very lonely. It's all by itself. So there are 40 if it was single bonds. How many should I have? BR is worth 7. So 7 times 5 is 35. Plus 5 is 40. Nice. What does that mean? That's the number of bonds and dots I need, which I don't need any. So 5. It's 5. I need 5. Why is that important? Because on my parent geometries, if it was 4, don't draw this. If it was 4, up, over, out, away. If it was 3, it would look like that. If it was 6, up, over, or up and down in a square. Like, it's only certain shapes. In this case, it's 5. So 5 is a vertical axis, and then what shape in the middle? Triangle. And how I remember that is I already did the vertical axis. That's 2. There's only 3 left. 3 is a triangle. So over, out, away. Now I care about what goes on those bonds. And in this case, they're all BRs. Whoa, okay, that's not good. Okay, parent geometry, it's whatever shape I did from the parent geometry, like the actual 5. So it's worth 5. We call that trigonal, because there's a triangle in the middle, and then there's 2 pyramids. So it's bipyramidal. Because there were no lone pairs, the actual geometry, or the molecular geometry, sometimes it'll say molecular, is the same. I can't fit it next to each other, so. Hybrid, 5 clouds, always say S. You can only say 3 P's, then you got to start saying D's. So S, P, 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 D, or S, P, 3, D. Oh, shoot. Flip over quickly. With just one quick thing we should do. Bond angles. Not a big deal. First, put a little mini star, I forgot about this, on the triangle, and put a little mini star on the axis there. If there were lone pairs, that's where they would be. And the reason why is that they're as far away as they can be from each other. Lone pairs take up the most space. So they want to be as far away as possible for the repulsion. But just understand, this is perpendicular, so this is 90 degrees. And this is a perfect triangle, so this is 120. And these are all 90. Because it's a one big square after square, so it's all 90s. So 90s and 120s for the first one, and just 90 for the second. On your sheet, it'll say a 180 as well, but it's not a big deal. Okay, sorry, we got to get back. Let's speed up here slightly. So the bond angle, it's the 90 and 120. Doesn't matter the order. All right, lastly, this is probably the hardest part for you the first time through. I don't care about the 3D anymore. I just care about that where they are. So I'm not going to draw it like, don't draw it like this. Like all of a sudden, now there's 5. Like, woo, it's a person. And you start making hands and feet. And, like, that's not what it looks like. You still got to make it look the way it's supposed to look. An axis with a triangle, but I'm not necessarily caring about the 3D part, as long as I have the bonds in a overall location. Quickly draw what was on there. Okay, you're doing great. We just got to finish this up. I got to draw the bond dipoles towards the one that's going to pull harder. The one more to the right and up will pull. Well, they're on the same line, but BR is more to the right. So you'll quickly see that these are all going basically in opposite directions. So this is very symmetrical. So it is non-polar. We got to hammer out these other two because these two will give you a lot of assistance when you're looking at this. Okay? It's all about comparing and contrasting here. Let's take a look at the next one, please. This one. Like last time, each line is technically holding an F with dots already. Like this. So that's 32. Why? 8 times 4. How many should I have? 4 times 7, because fluorine is 7, that's 28. Plus another 8, because xenon is a noble gas. So 8 plus 28, it's 36. What? Negative 4. You don't need to sit there memorizing this. What does this mean? Your picture has to be V, but my picture's only that. I'm short by 4. If you're ever short, what you do is you add electrons. If you are short, you have to add electrons. So how many clouds do I have? Well, I have 4 bonds, so that's 4 clouds, and then each pair is worth a cloud. So I have 6 clouds. Oh, 6 clouds. Immediately, I put Xe in the middle. What is 6 clouds? An axis with a square. The lone pairs go as far away as possible from each other. So it'll look like that. Wait, you just drew the axis with the square in the middle, and then you cared about the dots and the atoms. Yes, I'm always, when I have 6 clouds, I'm always going to draw the axis with the square. I'll worry about the dots and the atoms later. Parent geometry, it was 6, so it's an automatic octahedral. But the actual geometry does not include dots. So what is that? It's a square, and it's in a plane, so it's square planar.
Could you guys pass those down, please?
SP3D2. Right? SP3D2. Angle 90 degrees. And then just redraw like this. Kind of looks like a cat. Sorry. Saw that last hour. I'm like, what? Whiskers. What are happening in all those dipoles? They look like they are canceling out. So that's nonpolar again. It's very symmetrical. We got to get to the last one, so stay with me, please. Do not pack up early. We are fine. Still got 3 minutes. That clock's rolling. So that's another nonpolar one. Okay. The last one. SE would be in the middle. Those lines are worth 8 each. The line, like, well, no, lines are only worth 2. I get it, but I'm pretending that the F's are there with the dots. What you need to do is your center atom still needs to have an octet. So I still need to add these 2. If you forgot these 2, I'm going to do this 2 ways. So if I do this, this is 8, this is another 8, that's 16, 18, 20. How many should I have? SE is worth 6. F is worth 7, so 7 times 2 is 14, plus 6 is 20. I had a student the other day do this. I thought this was really interesting. What if you don't put the dots on the middle? You forget. If you count this up, check this out. It's worth 16. Oh, -4. What does -4 mean? My picture needs 2 more dots. Oh, I get there no matter what. What is that? 4 clouds. Oh, 4 clouds. That's tetrahedral. Up, over, out, away. Right? I'm making that the tripod. What do I have to put on there? 2 lone pairs, 2 atoms. Okay, notice what I'm doing. I draw the structure, and then I draw the atoms and the lone pairs. So this is tetrahedral. What's that actual shape? I cover up those dots. What does that actually look like? No, there's 2 of them there. It's bent. It's bent. This is an SP3. If you remember 109.5, every time you add a lone pair, it pushes it down by 2. So 109.5, 1 lone pair, 107. 2 lone pairs, 105. And last thing, you're doing great. We still got a minute. Just draw only the structure now. Who pulls harder? F. Those both are going down. So I can draw an overall big arrow, which means it's polar. Try to do the things to the right of the line, please. You got another worksheet. It's not due until next week. Your job right now is to work on molecular geometry 1 and finish up the lab that you've had 11 days to work on. Hopefully, we're getting it done. So, have a great day. Thank you, guys.